So let's think about a puck which has mass m circulating on a frictionless table like this, and the puck is on this circular motion by the help of this tension in the string, which is tied to a fixed point on the table. By the way, this is supposing that the puck is moving on a horizontal surface, and as I said, the surface is frictionless. So once you give some initial circumferential speed, the puck will move in a uniform circular motion. And we know that for a uniform circular motion, the centripetal acceleration is just equal to the circumferential speed squared divided by r, where r is the radius of the circular motion. So we will analyze this motion, and we will try to apply the Newton's second law for the circular motion. But in order to analyze this motion, or write down the Newton's second law for this circular motion, uniform circular motion, we have to tell that it is best to choose the coordinate system which is not y and x standard Cartesian coordinate system. Let's choose the polar coordinate system, which we use the angle and the radial distance as new coordinates, not x and y, but we use r and theta to define the kinematics of the motion in the circular motion. Well, why do we do this? Why don't we use analyze x and y, or let's say, since we are going to write down the Newton's second law, which is force is equal to total sum of all forces is equal to m times the acceleration. Let me write this over here. If you analyze the Newton's second law, you write down this Newton's second law for the Cartesian coordinate system. You have to decompose this equation into x and y components. You will have fx m times ax and fy m times ay. So you will have two equations. But if you choose the polar coordinates, you will see that you will only have one component of the motion, because there is no change in the radial distance. Okay, the magnitude of r is going to be constant all the time, because this is a uniform circular it's a circular motion. So the object is moving on a circle, and the circle is a fixed radius. So that means r is not going to change. The only thing is that the theta is going to change. And also we know that if this is a uniform circular motion, that means it has a constant speed. All right, this velocity vector is, first of all, is going to be always perpendicular to the position vector all the time, wherever it is, wherever the object is. Always the circumferential velocity vector is always going to be tangent to the circle, and r is going to be always perpendicular to the circle. And the thing is that I was talking about this position vector, which is going to be always having the same magnitude all the time. Although the position vector just rotates, it doesn't change its length, right? But theta is going to change, and we know that for a uniform circular motion, the rate of change of this theta is known as omega, and this is just angular speed. Okay, and we only think that the case where omega is constant. That means it's a uniform speed or uniform circular motion. And v is going to be fixed. The magnitude of v is going to be fixed. Of course, the vector is going to change, but the speed is not going to change. And we have just discovered that there's a relation between v and r. V is being the speed of the circumferential velocity, and v is always going to be equal to omega times r. Well, omega, which is the angular speed, is in going to be taken in units of radian per second. Okay, let's write down this explicitly. Radian per second. This is the unit for omega. Okay, but you know that the radian is not a unit. It's not a physical unit. It's just a number. So in fact, omega has 1/second, and 1/second, and this is has the unit of meters. So speed is going to be having the order, the usual unit, which is meter per second. So, okay, I was discussing about this motion of the puck, which is, in a uniform circular motion, and I told that in order to keep this puck on this circular track, we have to provide some tension on this string, which on one hand it is tied to the puck, and the other end of the string is just fixed at the center of the circle. And you will see that there is going to be always a tension or the force on the string, which is towards the center. Okay, and this is the only way to keep the puck changing its velocity all the time. It's going to change its velocity vector all the time, and we know that whenever there is a change in the velocity, there is a non-zero acceleration, and whenever there is acceleration, there must be force because of the Newton's second law. But as I said, I will write down the Newton's second law not in the xy coordinate system or Cartesian coordinate system, but I will write down the Newton's second law for the polar coordinates. So for the polar coordinates, the Newton's second law is going to be the force which is on the radial direction is equal to m times the centripetal acceleration. And we know also that the acceleration is toward the center, because if you think about the motion of this puck, it is always changing its velocity toward the center. That means the acceleration is going to be in this direction. So this is the direction of the acceleration. It's going to be along this string direction, but it's going to be toward the center, radially inward. That means radially inward. Okay. So I just wrote down the magnitude of the Newton's second law, the magnitude of force, the magnitude of acceleration. You have to put these vector signs over here. You have to put this anyway. But we know that the direction of the force is always toward the center. Also, the direction of the acceleration is always toward the center. For polar coordinates, we usually take the positive r direction to be radially outward, right? But if you put a minus sign in front of this component of the force or tension, which is along this radial direction, but it's inward, we have to put minus sign. But we know that the acceleration is always also inward, so it will take also another minus sign over here, so that the both minus signs will cancel out. So eventually we will have the scalar or the component wise, the component equation, Newton's second law, is going to be Fr m times AC. Okay. Well, sometimes in some textbooks, this FR is just, for this puck, for example, for this special case, for the special motion of the puck, the motion is provided by the tension of the string. You will see that this F is just replaced by T, which is for tension for the string, and M times A. Sometimes you also, in some textbook, A is going to be, typed as AR, R being the radial direction, okay? Or in our book, it's written as an A centripetal, AC, okay? They are both referring the same thing anyway. Okay. So, well, of course, in some cases, forces on the object might be radially, not only the tension, but some maybe other forces during along this radial direction. In that case, we have to put this sum sign over here. Sum of all radial forces is equal to mass of the object multiplied by its centripetal acceleration for uniform circular motion. Okay, this equation holds for uniform circular motion. The object is having a constant speed. It's having this circular motion, but it has a constant speed. That means its acceleration only in the radial direction. There is no any other acceleration component, tangential acceleration component. In that case, you will have a non-uniform circular motion. So this equation, all the forces acting on the object, which is on a uniform circular motion, this holds for uniform circular motion. Okay. The other thing that while this object or puck is circulating uniformly, at some time, if you just cut the string, all right, if you break the string at some point, so let's say at this point, from this point on, if you want to ask yourself that how the puck will continue its motion, since once you just cut the string at this point, there will be no any force acting on the object, on the puck. So it will go with this. There are some other forces that, for example, there is this weight of the puck which is downward, and also the normal force which is acting in this direction upward in relative to the surface. But since this normal force and the downward gravity force are just canceling each other practically, and also there is no friction, practically there will be no any force acting on the object from this point on where the string breaks. Okay, in that case, if you ask yourself that how is the puck will move, continue its motion, since according to the Newton's first law, if there is no any force acting on the object will move at a constant velocity without changing its direction or without changing its speed. So from this point on, whatever the tangential or circumferential velocity vector at the point where the string breaks, the puck will go with that constant velocity at this point, and without changing its constant velocity from this point on, the puck will move on the straight line in this direction. Okay, and it won't change its velocity vector, it won't change its direction, so it will just having a constant velocity motion from this point on. Okay, this is just an observation we have to make. So in order to keep the objects in a circular motion, you must provide some force, and whenever there is this force is just cancelled, the object will move on a straight line. Okay, now let's think about a very special type of uniform circular motion, which is called conical pendulum. and I will try to show you what a conical pendulum is. Simply, we have a mass, an object, which is tied to a string like this, and we just, let me show on this another small video. You just hold this object from one point on the string and try to circulate the object like this. Okay, what you see from the side views, this is the conical pendulum, but it looks like a simple pendulum, but if in fact it's not. If you look at this from side view, it looks like a simple pendulum, but if you look at this from top view, you will see that there is this object circulating around some fixed point on a plane. Okay, from top view it looks like a circular, uniform circular motion, but from the side view on the smaller video, you see that it looks like just like a simple pendulum. So this is called the conical pendulum, and let me just give you the sketch of the conical pendulum. Alright, so this is it. So this is the side view. You see one end of the string is just attached to a fixed point. It was my just hand, I was holding it, and on this picture this is the fixed point of the string, and the other end is just attached to this mass, and the mass is just doing this uniform circular motion on a plane which is parallel to the plane of the earth, but from this side view, while the object is circulating on this plane, the plane of the board, the object will go in this direction, like swinging back and forth, just like a simple pendulum. Okay, so at any time, of course, during the motion, the object will be pulled in downward direction by the earth because of its weight, which is nothing but m times g. Okay, and this force is going to be always downward, and the other force that acts on the object is going to be just the tension in the string, okay, which is tied on one end to the object, and the string is tied to a fixed ceiling at the other end. And as I said, while this object is circulating, well, it looks like an ellipse on here, but it's because of the perspective. In fact, this is a circle, all right, which has a fixed radius r, and there is this angle that the string is making, this angle with the vertical direction, okay, downward direction, that is the direction of the gravity, and this angle is always going to be again fixed. It's not going to change, although the string will rotate around this vertical line. This angle will be fixed, it will not change, okay. And this is just the free body diagram. This is the real scheme of the motion, and over here we have this free body diagram. As I said, there is only two forces acting on the object. In fact, at this point it looks like just a free body diagram because we have the object and we have only the forces. And on this picture you see this tension in the string is just decomposed into vertical and the horizontal components, and since the angle between the string and the vertical direction is just theta, these components is going to be just t times cosine theta, which being the vertical component of tension, and t sine theta being the horizontal component. So why we are decomposing this tension in both directions, in the horizontal and vertical? Because we will analyze the motion in just the Cartesian coordinates. Well, this time we are going to use, Cartesian coordinates because we are going to analyze the motion not on the circular plane but on this plane which is perpendicular to the circle of rotation. Okay, and at any point, the other thing is that at any point during this motion, these vertical components are not going to change. In fact, the magnitude of these vertical components will not going to change, because theta is not going to change, although the object will circulate. This angle that the string makes with the vertical line is not going to change. So we can analyze the motion on a perpendicular plane, perpendicular to the circle of rotation. Circle of rotation is one plane, and this is the plane that is perpendicular to the circle of rotation. Okay, so you can just write down, Newton's second law for that coordinate system. Y and x is just a plane which is perpendicular to the circular plane. Okay, so if you write down the Newton's second law for both directions for y and x, you will see that for, let's write down for y, y being the vertical direction, and there is no any motion of the object in the vertical direction, although it moves all the time. It doesn't move in this direction or downward, upward or downward. The object is not going to move upward or downward, right? So in the y direction, if you write down the Newton's second law, sum of all forces in the y direction is going to be m times the acceleration in the y direction. But since there is no motion in the y direction, this is 0. So sum of all forces acting on the y direction is 0. And if you write down, take the upward direction to be positive, t cosine theta is going to be plus, and m times g is going to be minus, and this is going to be 0. So from this, t cosine theta is equal to m times g. This is the first equation that we obtain. If you write down the motion in the x direction, well, now this x is being in the direction of r at this position of the object. The x-axis, and at this special position of the object, and this axis which is shown as r, which is nothing but the radius of the circle. So we can just put, instead of x over here, put r, because this direction is nothing but the axis which is on the circular plane, right? And we can always write down the forces and everything in the radial direction, because the object is moving in a circular direction, circular motion. So why not we just write down the force equation in the radial components? So when you look at the object, its motion in the vertical plane, okay, in the circular plane, let's say, this t sine theta, wherever the object is, this t sine theta force is going to be always toward the center of the circle. If the object is over here, the t sine theta is going to be just toward the center. if it's over here, the t sine theta is going to be toward the center. So as you see, this t sine theta force component is always showing the same direction in the polar coordinates. So you can write down the Newton's second law for this. In that case, let me first write down the general expression for the radial direction force. The sum of all forces in the radial direction is just the mass of the object times the centripetal acceleration. Do we have now a non-zero centripetal acceleration? Yes, because the object is doing the circular motion. Okay. And what is the force that is providing this circular motion to the object? It is nothing but not the tension T, but it's this component of the tension, okay, which is nothing but T sine theta. And T cosine theta is nothing to do with the circular motion, because it's always perpendicular to the plane of the motion. So instead of this part over here, we only write down T sine theta and m times. So instead of AC, we can just write down the constant speed squared divided by the radius of the circle, which is nothing but this distance from here to here. It is the radius of the circle. So you get these two equations, 1 and 2. So from these two equations, we can express the speed of the object in terms of the geometry of the geometrical parameter of the problem. Well, the problem gives you the length of the string as this capital L, okay, and this angle theta to be fixed. Well, it's not going to change during the motion. So in terms of L, theta and G, you will see we can express this constant speed of the conical pendulum like this. Using these two equations, we can divide this equation and this equation 1 divided by 2 like this, okay. The first equation is T cosine theta, and divide this by T sine theta. Or let's do this. Let's do the other way. The equation 2 divided by equation 1. T sine theta divided by T cosine theta. We divide the left hand sides to left hand side and right hand side to right hand side. T cosine theta. This is equal to mv squared divided by r, because T sine theta is just equal to mv squared over r, and T cosine theta is just equal to mg, right? So these t's will just cancel out, okay. We will have just tangent theta on the left hand side, and also m's will cancel out. We will have just v squared over r times g. But r can be expressed to be the length of the string multiplied by sine theta, because this is nothing but a right triangle, and L being the hypotenuse of this right triangle, and r being the side which is opposing this angle theta. So just we put, instead of r, we put L times sine theta, and we have over g over here. So from this equation, it's very straightforward to write down v, the speed of the circular motion of the conical pendulum, being L times g times sine theta multiplied by tangent theta, and in square root, of course, in square root. So this is the expression for the circumferential speed for an object which is moving in a conical pendulum.